Hello, this is Jack Jackson. In this video, we're going to start seeing some examples of writing some proofs. So I think this is probably a good time to show you the appendix and show you about navigating the document here. So if I hold down Control and click on a link like this takes me to the appendix in the document here. So the appendix is got our official list of propositions, definitions, and the postulates. So here's an introductory statements here. And these are the things, we've already talked about these. Here are undefined terms. And in red are our postulates. Definitions are in blue. Some notes are in green. And propositions are in black. So here we have our first 9 postulates, which we've talked about earlier. And we have our first few propositions. Here are the first 5. Now, we're going to actually start with by proving 2 through 5 in the next, we'll do one video on each. But we're postponing the proof of Proposition 1. Proposition 1 said there exist at least 6 distinct lines and 4 distinct planes. And that one is an existence proposition. The proof of it follows a little bit different form than a normal proof. So we're going to postpone its proof until next week, a little bit later in the notes. But we're going to work on these. Now, Proposition 2 has been changed here when we start talking about an unbounded and a bounded distance metric. That's something we'll do a little bit later on. So that's a tweak that we're going to do to Proposition 2. Okay, so let's go back. Every now and then there are these links for the title page and appendix. If I do Control and click on this, I may have to click on the word title, but I click on that, it takes me back to the very beginning of the document, which gives me easy access to the table of contents, and then I can go right back, again holding Control down. The hyperlink table of contents sends me back to where I want to be. All right. So let's go ahead and start with writing out a proof of Proposition 2. Now, Propositions 2 through 5 all can be written in the form if hypothesis, then conclusion. So, for example, Proposition 2, if 2 distinct lines intersect, then they intersect in exactly one point. So the hypothesis part is that you have 2 distinct lines that have a non-empty intersection. And the conclusion part is the intersection must be exactly one point, a set of exactly one point. So here's what I'd like you to do, is see if you can write the proof of this yourself. You can only use the postulates that we've used so far. Okay, this one doesn't depend on any earlier proposition. So again, you can go back to the appendix or earlier in the notes, either one, to see the list of postulates that we can work with. Try this yourself. Try to write out a multi-column proof of this. And even if it's a failed attempt, that's okay. Learning how to do this will be helpful if you try it, even if it's not correct. And I'll give you a hint. We're going to use a proof by contradiction for this one. So what I'd like you to do is try this one yourself. Come back then and look at my example after you tried it yourself. Press pause now. Well, you're back, so I hope that means you made an attempt at this, but even if you didn't, let's go ahead here. So one useful form for working with propositions is to write it like this. Given, hypothesis, prove, conclusion, and then proof. So given, distinct lines L and M, notice I named them, such that their intersection is non-empty. Prove, the intersection of L and M is exactly one point. And proof, and then I gave the reader a heads up that it's by contradiction, although that's not necessarily necessary. Now, we have a column, just a number, 1, 2, 3, 4, because this one only has 4 steps to it. We have our statements, our conclusions, and in the left column and the right column, we have reasons or justifications for each of those steps. The stuff with the darker background, that's automatic. The first statement will be the hypothesis. Let L and M be distinct lines that have a non-empty intersection. That's the given hypothesis, and that's the reason for that statement. The last statement will be the conclusion of what we're trying to prove. The intersection of L and M is exactly the set containing only the point A. Only one point. Okay, so let's see how do we get there. The other steps will be links in a chain that will get us from the beginning to the end. Okay, so for statement 2, we're going to say there exists a point A on both L and M. Statement 1 is why we did that, and the definition of what we mean by non-empty intersection. I guess technically we're using the idea that we're actually using an earlier postulate that says that lines and planes that are geometric figures, which the definition says they're sets of points. But we're going to use those earliest two postulates without really referencing them. Now that we have a point on L and M, now let's do the proof by contradiction. Suppose there exists a point B such that B is not equal to A and B is on both L and M. Now, this thing actually doesn't exist, but we're going to suppose that it does for later contradiction. Normally, you can't just put a statement in there without a reason. So if we just suppose it exists, this is going to be for later contradiction. So the reason we put is supposition for later contradiction. Now, let's look what we've got. Statements 2 and 3 contradict the at most portion of postulate 6. Postulate 6 says, given any two distinct points, there exists exactly one line that contains both of them. Therefore, the supposition in statement 3 has to be false. The little black box at the end, little black square, we're going to use that symbol at the end of every proof. This replaces the Latin phrase quod erat demonstratum, or QED for short, which translates as that which was to be proved. Or as Porky Pig said, that's all, folks. It's telling us this is the end of our proof, okay, that we've done what we set out to do. So again, notice that these shaded portions are automatic. Over 99% of all proofs, the first statement will be the statement of the hypothesis, the reason will be given hypothesis, and the last statement will be the conclusion of the proof thing we're trying to do. What you absolutely cannot do is state the whole proposition there as a statement. So if you look back at this, this really only required postulate 6. Actually, it only required half of postulate 6. A weakened version of postulate 6 would say, given any two distinct points, there exists at most one line that contains both of them. And then the other half of postulate 6 says, given any two distinct points, there exists at least one line that contains both of them. As long as you've got postulate 6 or even a weakened version with the at most part only, then this proposition here is true. So in a way, it's kind of a different way of rephrasing postulate 6. All right, let's try another one. Okay, now that you've seen a model, let's see if you can do this one. If a line intersects a plane not containing the line, then the intersection of the line and the plane is exactly one point. See if you can prove that one yourself. And come back to the next video to see the proof.